Hello everyone, welcome back to my channel, Predicting the Future. Today we'll continue our topic on Martingale theory on episode about conditional expectation. And I'll briefly go through what we're going to talk about today. We're going to talk about conditional expectation, how it's related to what we see in the traditional probability theory, elementary probability theory. We're going to see how it's related to the conditional probability from conditional expectation, and we're going to prove the base formula that we see in elementary probability theories. So first thing I want to talk about is what are the representations of conditional expectation, which we talked about in the last video, is a random variable. When the sigma field F was generated by a partition of sets from the space omega. For example, if omega 1, omega 2, and so on is countable finite infinite partition of this sample space omega, and also the probability of each omega I is greater than 0, then what is the representation of expected value of x given f? And the first thing what we're going to talk about is this is a representation of such sigma field f, which is a summation of some constant ci times an indicator of omega I, where the ci is expected value of x or integration on omega I divided by the probability of omega I. So why this is our candidate for the conditional expectation? Let's prove that. But before that, let's see what it means. So for example, given omega, or that omega belongs to some omega I, then our value of the conditional expectation, the random variable, will just be some ci, where the omega will force into the corresponding omega I. So, and the ci is just conditional expectation of x integration, the expected value of x integral on omega I divided by the probability of omega I. Think about our case where in a elementary conditional lectures, where we might have where the omega I is just, for example, x is less than some constant. So in that case, our omega or our sigma field f is just generated by where x is less than c and x is greater than or equal to c, two partition sets, and that's how we calculate our expected value, and that's just exactly what we see here. So that's intuitive understanding why this is the right candidate for conditional expectation of partition sigma fields. And then we're going to prove it. So first, we need to prove two things, right? Remember the conditional expectation, we have two conditions we need to prove. First, our candidate must be f measurable. Second, it has to be satisfying this integral equality for all event E in this sigma field. And that's what we are going to prove. So the first one, this is f measurable. Why? Because this function is just a summation of simple step functions where each step function is f measurable, because omega I is measurable. And each event in f is just a union of those partition sets, right? So that's generated by, because f is generated by those sets. So any event in F can be represented by a union of those partition sets, and and so the function our candidate for conditional expectation is just F measurable. And then we need to verify the second condition, which is the integral of our candidate over any set A is equal to integral of x over any set A where A belongs to F. So to prove that, we first look at A. So we know that A is a countable union of omega I. Therefore, the integral of our candidate can be written as integrator of omega I. So let's say A is a union of omega I j. Then this integral can be separated by each omega I because they're disjoint into this form, and if we multiply this into our candidate, what we left, because they're disjoint, each are disjoint, they only match when the omega I1 equals to some indicator inside the summation, and that will just be each of those will become Ci1 times Cij times indicator of omega ij. And what we left is that which tells us that the only thing we need to prove is that the integral of Ci on each omega I equals to integral of x on omega I dp. Once this is satisfied, this one will satisfy for what we need to prove here by A is because of A is disjoint of those omega i's. And so to prove that, this is the only thing we need to prove. And by looking at this one, Ci is a constant, we take out the constant. What we have here, the integral of omega I is just probability of omega I. And Ci, by what was given in our theorem, Ci is just condition expected of x integral on omega I divided by probability of omega I. And the probability of omega I just cancel out. What we left is just the conditional expectation of x, the expectation of x integrating on the subset omega I. And that is exactly integral of x dp. And so that proves this one equals this one. And that proves our theorem. So so by using this one, we can see that so by using, we're going to use that one and see how the conditional probability formula comes from. So remember, the probability of A given a sigma field F is equivalent to conditional expectation of indicator 1, indicator random variable on set A. So this two is equivalent. And if we let F to be a sigma field generator B and B complement, and then by the theorem above we just proved, then probability of A given sigma field F is just a summation of this form, and this is what we just proved in the last theorem. In the last theorem where we have here the x is just indicator, and x is just indicator random variable, and that becomes this form. So what this tells us is, given, for example, we are talking about conditional probability. So we know, for example, we know some event happens, and happens that omega belongs to a set B. So given experiment omega that falls in B, then this random variable will produce a constant which is probability of A intercept B divided by probability of B. So that is exactly what we see in elementary conditional probability theories, and that is used to define the symbol of P A given B. And that is when our event, our observation omega, falls in B, then the conditional probability of A given B is coming from what we have seen here. So that's how we find how the elementary conditional probability formula was derived from in measure theory. Well, if in set theory, it's also very easy to understand, but was not rigorously proven. But here we are proving the formula for conditional probability rigorously here. So the next one is we want to also prove the Bayes formula, using the definition of conditional expectation. So what we are stating is that for any B belongs to a sigma field F, the probability of B given A is this form. So that is integral over B of the PA given sigma field F dP divided by integral of PA given F or integral on the whole space omega. So we want to prove that this is a candidate. This is a candidate for our conditional probability of B given A. And we also want to prove that when the sigma field F is generated by a partition, then our formula for this formula will be just reduced to our Euro Bayes formula, which is just be PA given BI times B PBI, and the denominator will just become a summation, which is very easy to prove because what we have here is just constant times probability integral of BI, and the denominator is just be a partition of omega into the BI's, and this will just becomes a summation of this form. So what we have to prove is this one. So so let's first look at the integral of PA probability of A given sigma F on B, and we want to prove that this is equal to PBA times this one. So the integral of PA given B given sigma given F on B is just integral on expected value on indicator function, and that is just probability of A intercept of B, because this is just same as integral of function 1 on indicator function 1 on set A. And the other side is PBA times this one. I want to prove that this is the same of PAB, P intercept AB. And so the multiplication of these two is by definition what we just seeing in here. PBA is just P intercept BA divided by PA, and this one, by the definition of conditional expectation, the inside of that is just indicator. This will just equals to integral of indicator random variable on A, integral on space omega, and that would just be probability of PA. And this one cancel out, what we left is just probability of B intercept A, and that proved what we need to prove for this formula and further for this formula. So that's the proof for the Bayes formula. I hope you guys like it. Bye.